Okay, now I turned on that recording button. I forgot it. Okay, hold on. Okay, so hybrid power grid or hybrid power sources means there should be the conventional synchronous machine plus the renewable sources like wind energy, photovoltaic system, other form of energy storage systems, etc. So that is called that hybrid power grid. So therefore, for example, here you see this is one of the example of hybrid power grid. Probably before I have shown you this diagram. Here, as you can see, there is conventional system which is SG. This one, SG means that synchronous generator. And then, as you can see on left side, there is 2 megawatt wind turbine system, and then 2 megawatt photovoltaic system. And then on energy storage example, for example, here supercapacitor battery energy storage. And all they are connected at this common bus, and they are connected together with that synchronous machine system. And all this together, they are powering that distribution grid. And then, that we are assuming that there is SCADA, supervisory control and data acquisition system, that is continuously monitoring and taking and exchanging information with the whole network. So because here there is a mixture of power sources or energy sources like synchronous machine, wind generator system, photovoltaic system, together with the energy storage, this is the hybrid power network. Now, here is the distribution network. Even depending on the capacity of these renewable sources, in this case, in this example, I am showing you only like 2 megawatt, that capacity, but they can be several hundred, like 200 megawatt or 300 megawatt, which we can say like wind park or wind farm or solar park. Or, you see, so in that case, they could be connected even at the transmission level. So in this case, I have confined it up to 11 kV. As you can see, synchronous generator secondary voltage 11 kV. This means at this point, which is called point of common coupling PCC, 11 kV. Similarly, as you can see, all sources are producing 11 kV, 11 kV, 11 kV. So therefore, clearly, this is at the distribution level. But of course, you have noticed that synchronous generator typically connected at the transmission level. Accordingly, these renewable sources can be connected at the transmission level as well. So when they have the very high rating, like more than 100 megawatt at least, typically 200 and 300. Now, whatever they are connected at the distribution stage or at the transmission level, there can be stabilities. Now, the stability can be the cause of these sources or at the distribution level or transmission level, or due to the any fault on the synchronous machine. So therefore, whatever the location and whatever the type of the fault is, disturbance is, the whole network will be impacted. And each sources, photovoltaic, wind, synchronous machine, each will behave differently. So that's why that will be looking that today, what is the stability and then dynamics for that hybrid power grid system. Now, so far we discussed a lot. We concentrated mainly on that synchronous generator system, synchronous machine-based system. But in the system, there is wind generator. So we'll be looking some of the issues and then dynamics of that wind generator and photovoltaic system. And then we can see the interaction for the entire network. So for example, some of the common stability problem that arises from wind generator system. For example, a fault happened at any of the point. Here fault happened or here fault happened, or fault could be on this common bus point. But what is the impact that goes on the wind generator system? So you see, I have written that wind generators have stability problems similar to the transient stability of conventional synchronous generators. So this means that this is not that only the synchronous generator will be affected. Similarly, the wind generator will also face stability issue. And what can be the issue? That during a fault in the power network, rotor speed goes very high, active power goes almost zero, and terminal voltage goes low or collapses down. So you remember that before we discussed the impact of fault in case of the induction generator. And you notice that there is some difference between synchronous machine and induction machine. Therefore, in case of wind farm or wind turbine generator system, mostly induction machines are used. And because induction machines are mostly used, that's why you see terminal voltage go low or even they can be collapsed down fully. Active output power can go very low because of that induction nature, because they draw always reactive power from the system. And then usually the wind generator is shut down during these emergency situations to protect the generator. But in recent tradition, in recent age, what is the technology? Not to shut down the wind generator during a disturbance or fault, but keep it connected to the rest of the grid through the appropriate control. This means typically wind generators are connected to the grid through power electronics. You have to control the power electronics. You have to apply the proper technique, appropriate or the suitable control technique so that they does not get disconnected during the fault. They should always remain connected, which is called like fault ride through capability. But if you say, when I say that usually wind generator is shut down, this is not recent tradition, like at least 10 years back. In most cases, now one thing, when there is, tornado or hurricane, then that is by force wind turbine is shut down to protect the blades, to protect the wind turbine system. But in this case, this shutdown means it is not because of storm, it is not for the protection of the blade, just it is disconnected to prevent this situation because terminal voltage is going low or collapses down. That will impact the rest of the grid. Other system will be affected. That's why, like at about 10 years ago, until kind of 2010, the tradition was to shut down. But then recent tradition, in recent days, it is not, no, it is not wise to shut down because if you shut down, then again you have to reconnect it. That has some issue. That's why recent tradition, with the help of the power electronics control, keep it connected. And that is the smart way, and which is called fault ride through capability. Now, to understand these interactions, I mean, those who have joined that modern grid with renewables class, we extensively discussed various type of wind generator system. Here I will just show you 2 to 3 slides to understand that dynamics. I think everybody were in the class except Sindhuja and Lakshmi. So you are not in that modern grid class that I covered in the spring semester this year. So I mean, these things will understand you the dynamics or the stability issue when there is wind generator in the system and how they may affect the rest of the grid. So therefore, briefly speaking, wind turbine system, wind generator system are two types. One is called fixed speed, and then the other one called is the variable speed. So fixed speed mean this does not mean that the wind is fixed. Wind speed is always varied. I mean, for a very short time, you can assume 1 minute, 2 minutes can be constant in a particular area. But in reality, like wind speed is always varying. It is intermittent in nature. It is stochastic in nature. So that's why fixed speed wind generator, this does not mean the wind speed fixed. The meaning is that with the help of control system, you are keeping the shaft speed almost fixed or almost constant. That is the meaning. So therefore, for example, here you can see this is that wind turbine blade, and then there is gearbox. There is gearbox because you have noticed that typically wind speed is very low, and then the gearbox will speed up, increase that speed. I mean, the similar function as to the transformer. So it can convert low voltage to high voltage. In this case, gearbox can increase your speed from low speed to high speed. And that is done so that it can provide a almost constant speed. And why it is done? Because if you remember that synchronous speed equation, N is 120 f over p. So for example, your frequency is 60 hertz. And then if your pole number is 2, then you need a speed of 3600 rpm. Now, because the customers will be connected at the grid side and the customer requires 60 hertz frequency, that's why you have to maintain a constant speed. And that is the reason, and the name goes according to that, fixed speed wind generator system. So meaning that whatever the wind speed is here, and then that is increased, and with the help of mechanical control system, that fixed speed is being maintained. But because you are maintaining a fixed speed, this is the shaft of the generator that is facing huge stress. You see that I have written for you. Due to fixed speed, the turbine faces much stress because it is not flexible. So whatever the wind speed, high wind speed, average wind speed, and low wind speed, always you are trying to maintain a constant speed here to so that the grid gets always 60 hertz frequency. I mean, depending on the country, it can be 50 hertz, that is different. But for United States, here it is 60 hertz. You want to maintain 60 hertz. Consequently, here you need that speed, 3600 rpm. So therefore, and then in most cases, and what is the region, then what should be the type of that generator? As I said that induction generators are mostly used with wind generator. It is that squirrel cage type. Say, you know that early of the semester we mentioned there are two types of induction machine. One is called squirrel cage type that provides fixed speed, and then there is other is wound rotor type that can provide variable speed operation. So therefore, when it is fixed speed wind turbine system, meaning that the induction machine is squirrel cage type. Now, whether it is squirrel cage type or wound rotor type, as we discussed before, induction machine always draws reactive power from the system. And that's why it has that low lagging power factor. You see, voltage might go down even during the steady state condition. That's why, you remember, we discussed we have to connect capacitor, which is called compensating capacitor. That capacitor compensates that low reactive power factor and maintains a rated voltage here and the rated power here. So everybody, could you follow me?
Yes, Dr. Ali.
Yeah. So Lakshmi and Sindhuja. So then this slide is new, but I think rest of the everybody joined that modern grid class, so they already have looked. And then I have written down the necessity of having that compensating capacitor here. Their function is to achieve a unity power factor in order to maintain rated power and rated voltage even at the steady state situation. Now, if there is any fault on the connected grid system, then this capacitor is not enough. You need STATCOM, SBC, other type of capacitor bank. Those are different things. But this capacitor is needed at the steady state when there is no disturbance, nothing. I mean, wind speed is changing. We are not assuming that wind speed change is a fault or a disturbance. That is coming from the nature. You have no control with that. By the disturbance, we are telling that if there is anything on the grid side, any fault or any short circuit, open circuit, other type of disturbance. So therefore, briefly, you keep in mind, this is the feature of the fixed speed wind generator. It will have a squirrel cage type of induction machine, and they are directly connected to the grid, direct connection. And rotor speed is determined by grid frequency, and because of the having fixed speed, turbine faces a huge stress. And then now what is that variable speed? And then we will say some example, then that will help you to understand the dynamics for this renewable based hybrid energy system. Now, variable speed wind generator. So as you can see, the fixed speed versus variable speed. In this case, that rotor speed is variable. This means that in this case, whatever the wind speed is, the rotor system is adaptive to that changing situation. It is not like fixed, unlike the previous situation. So that's why the name goes the variable speed. Variable speed means wind is varying, accordingly your turbine shaft is also varying. Shaft speed is also varying. So therefore easily you can understand, because the shaft is varying, it will produce the varying output, varying power, varying frequency. So because it is variable, so easily you can see that NS 120 F over P, EP speed varies. If your pole number is fixed, then your frequency will vary. But then as you can see here, the customers are connected at the grid. They need 60 hertz system here, whatever it is, because of that variable speed situation, they need 60 hertz here. So that's why, as you can see, for this type of structure, there is power electronics equipment like AC to DC converter. Then there is a capacitor which is called DC link capacitor, and then again converted back into AC, DC to AC conversion, and that provides that required frequency, for example 60 hertz. So therefore, as you can see here, the frequency is varying, and because the frequency is varying here, that's why you are rectifying it. You are converting from a varying AC into a DC. So as you can see, because it is DC, so now it became independent of frequency. And then, but here the customer, this is AC. This is the transformer symbol. So definitely this side is AC. Again, you need AC. That's why you are converting back from DC into AC with the desired frequency. So therefore, the required controller for this inversion system, it provides the required frequency and required voltage, which is needed at the grid. So therefore, this is done. As you can see, there are different type topology. All are example of variable speed. This is induction machine based, but these all are the synchronous machine based. Number B and number C, you can see there is a feedback path. Can you see there is a feedback path? That AC is again converted into DC, and that is given to the DC excitation system. This means these are that conventional synchronous machine-based wind generator system, and they require the excitation that we learn, like DC excitation, AC excitation, or static excitation. In this case, the input is taken from here, and then that is converted into DC, and that DC is provided to the magnetic field, which is located on that rotor body. And then the last AC example, this is permanent magnet synchronous based wind generator. That's why you see that feedback path is not given, because there is permanently magnetized pole. So you don't need extra or additional excitation. But in each figure, as you can see, these power electronics components are present. So that's why everybody, I mean, you will keep in mind, if it is variable speed wind generator system, then definitely it will be connected to the grid with the help of the power electronic device. And why that is needed? Because you are allowing the varying speed, your shaft system is varying. It is producing varying output, varying voltage, varying frequency. All quantity are varying here. But here you need the stable or constant frequency, constant voltage. That's why you are using this mechanism. Here the AC varying, okay, fast converting to DC. Let make it independent of the frequency. And then with the help of the required controller, you make it whatever you need it. That is the concept. So you see, I have written here briefly that variable speed wind generator is connected to the grid through a power electronic interface. So the generator is decoupled from the grid. This is generator, wind generator. that is decoupled from the grid. Here one type of frequency, but here is different frequency. In that sense, it is called the decoupled from the grid. And the frequency voltage are controlled by the power electronics. And it can capture more energy than the fixed speed generator. And it does not face much stage as it is adaptive to the variable wind speed. So as you can see here, we said, because we are by force, we are making the speed constant here. So whatever the wind speed, accordingly up to that it is changing, but on that side with the help of mechanical arrangement, we're maintaining a fixed speed. And that is causing to face it much stress. So on the other, and this means that we are losing some of the energy. When it has, high wind speed, it should produce much power, but because I am maintaining a constant speed, constant speed means, if you remember that voltage equation, 4.445 Fn k omega. So we are neglecting the sum of the captured energy. So that's why if you compare with that variable, it can capture more energy. This means that when it is rotating at low wind speed, accordingly it is producing power. When the wind speed is very high, accordingly it is capturing that power. And consequently, we are allowing here that variability of power. But in the previous case, it is fixed. Always it is fixed. So this means we are not allowing more than that power level. So we are losing some of the energy, wind energy. That is the meaning of this thing. And because it is adaptive, it is varying. When wind speed is high, then it is going high. When low, then low. It moderate, then moderate. So it is adaptive to the variable wind speed. That's why that this system, variable wind system, is preferred. It has some beneficial feature over that fixed one. So that's why this system is early. These days there is, nobody installed this fixed speed. It's still present, but if you prefer fixed speed versus the variable speed, of course you will choose this variable speed because of these features. Could you follow Lakshmi and Sindhuja?
Yes, Dr. Ali.
Okay. So
Yes,
now,
Dr. Ali.
okay. So therefore, these are here I showed you that example of induction machine based. And as you can guess, this is not a squirrel cage type. This is wound rotor type because we are allowing the bearing speed. So although simply it is written induction generator, but keep in mind this is the wound rotor type. And all these three configurations are for the synchronous machine based. The last one is for PMSG, permanent magnet synchronous generator. That's why you are not looking that feedback path. And these two are the conventional synchronous machine based. That's why there is feedback path, which is providing the required excitation to energize the magnetic field. Now there is one example of that variable speed wind generator, which is called doubly fed induction machine. Doubly fed. So if you see the structure, so far you see, these all are like unidirectional. So there was no feedback path from here to the rotor circuit. But in this case, you see, in one hand, it is connected to the grid through the transformer. And on the other hand, with the help of other transformer, there is feedback path via the power electronics that is feeding the rotor circuit. The outer rim is called stator and inner circle is called that rotor. So therefore, you see, from here, with the help of power electronics, the rotor circuit is being fed. Or in other words, from the rotor, with the help of power electronics, you are feeding the grid. So here, same thing, the stator is directly connected to the grid. So accordingly, it is called doubly fed. Two fed. Both stator and rotor have the connection to the grid. That's why it is called the doubly fed. Now, this is the most popular one. Although there is relative pros and cons between this doubly fed type versus this type, but this is the most preferred one, this doubly fed. The reason is that you see, here there is between stator and the grid, there is no direct power electronics component. But here the power electronics component is between grid and the rotor circuit. That's why here you need the power electronics. The requirement is about 33% of the machine's rating. But in this case, because those are directly connected, so as you can see, according to law of conservation of energy, because the energy produced here should be available here, and that should be available here. So that's why you need the power electronics that must have the capacity equal to the machine's capacity, because those are directly connected. In this case, you see, they are not directly connected. That is via the rotor circuit. So therefore, stator circuit has one power, rotor circuit has different power. Because it is connected or it is controlling the rotor circuit only, that's why the power electronics capacity here, which is about 1/3 of the machine's capacity. Because some of the power is exchanging through the stator directly. So in that sense, this power electronics device offers less cost. It exhibits less cost as compared to this direct connection. That's why this structure is more popular. And as you can see, again, here like there are AC to DC, DC link, capacitor, and then DC to AC inverter. So same thing is here, because this is transformer. So definitely this side is AC, then AC to DC, that DC link capacitor, and then again DC to AC, because rotor circuit is also AC. Both stator and rotor are AC. So, and then there are two types of function. Typically, as you can see, because they are connected to the rotor circuit, the controller for this AC to DC converter, they control the rotor speed and hence the active power. The controller for this conversion system, for this converter system, they control the grid voltage and power factor and hence reactive power. And then that DC link capacitor, they provide a balance between this converter and this converter. So those are the functions of this power electronics arrangement. So can you follow me?
Yes, Dr. Ali.
Okay. So therefore, this is in brief the basic dynamics of wind turbine generator system. You know that in the modern grid class, the other students are present. Like we discussed extensively, we spent a lot of time on the wind generator system. I mean, the few classes we spent here, just because we will be focusing on that stability. That's why we are trying to understand the dynamics and the essential features of those wind turbine system. So now that for the basics of solar system, so we will not go in detail, just this on this slide, then we will discuss some questions and numerical problems. So in case of the solar system, I mean, the main goal is to show that how the solar system is connected to the grid so that we can understand the dynamics during the fault situation, which is the transient stability case. Because we will be focusing on the transient stability, that's why we want to know what are the components there. So what is the dynamics there, how it is connected to the grid. So therefore, so you all know, for example, this is that solar system or area or panel, and that is connected to the grid with the help of first there is DC to DC converter, because you know that solar system produces that DC, it is not AC. That's why, and then that is very small. I mean, not more than 200 volt here, hardly 200 volt. In most cases, 100 volt, 150 volt. And then you need to boost up that voltage. So that's why this is DC to DC boost converter that raises the voltage. And then how much it is rate, it depends on that inverter capacity. And then again, that depends on what is the requirement on the grid. Accordingly, you have to put a step-up transformer, and that will govern the size of the inverter. And this inverter will govern the size, decide the size of this DC to DC converter and how much voltage is needed. Like all are interrelated and all are designed based of the best compromise, trade-off, and then cost effectiveness and economy. Accordingly, all are designed. So when I say that DC to DC boost converter, so then question is how much I will boost up. Is it 400, 500? It depends on the capacity of this. And again, how much is the capacity? That depends on the what is the capacity here and what is the size of the transformer. That is again dependent on what voltage is needed here, what capacity of the power is needed. All things are like related. So anyway, then here we are producing some voltage, for example, 150 volt or 200 volt, and you are increased at a certain level, assume that 400 volt. But then here again, you need a capacitor. I mean, I am not showing, I just wrote DC link. I mean, that will look like this type of capacitor. So that is that DC link. DC link means it has a capacitor that will hold that constant voltage. So you know the property of the capacitor in case of the DC. So it will reduce any ripple, plus it will hold the constant voltage, and also it will maintain a balance between this converter and this converter. I mean, similar function to this one or this capacitor. It's a balance between this converter and right side converter. And then because this is DC until now, so you have to convert into AC. That's why there is DC to AC inverter system. And again, there is sophisticated controller. I'm just showing, okay, there is controller here. Those are very sophisticated controller. And that controller can decide, or that controller will work based on the necessity, based on the requirement, what frequency I need here, and what should be my voltage. So that controller will determine that. So of course it is, on hand it is inverting from DC to AC, but you can say DC to AC with desired frequency and desired voltage. So that desired frequency and desired voltage is being decided or being controlled with the help of that controller. Now this controller, it can be that smart controller, accordingly the smart inverter. So the Lakshmi, like your topic is smart inverter. So here is like you have to show the smartness. You have to show the intelligence here, that it is not just you want to transfer DC to AC, you want to convert. You have a sophisticated controller. That controller can control the active power, reactive power, voltage, power factor, everything here with the help of this one to match or to meet the demand of that grid. So that's why it is called a smart inverter system these days. So then of course, here you need some sort of smart controller, smart converter, although this is just simply DC to DC boost converter, but still you need a good controller here. So
Okay,
Lakshmi,
Dr.
could you
Ali.
follow?
Yes, Dr. Ali, I will follow. I am following you.
Yeah. So therefore, here I wrote like simply controller, but that should be an intelligent controller, at least a basic nonlinear controller. Like for example, simply you can think fuzzy logic controller or neural network based controller. It should be a nonlinear controller or any data analytics based controller. Plus, when I say smart inverter, I mean, currently I have drawn the picture. You see, it is unidirectional. Always see my arrow. It is going from left to right. But when it is a smart inverter, it should be bidirectional. Like depending on the necessity, it should have the capability to send power in this direction also. And that's why it will have its smartness or the intelligent capability. So that
Okay, Dr. Ali.
therefore your focus will be mainly this on here. So here you will have all your work and then originality and novelty, and it should be bidirectional. Therefore, typically, whatever controller you use, if you use voltage source converter here, then that is, I mean, by default bidirectional. You just need a smart controller, intelligent controller. So therefore, initially you might try with conventional PI or PID controller, but then later you need to make an intelligent controller. And with, for example, something happened, fault happened, instead of using any other auxiliary device like an SBC, STATCOM, any energy storage, with the help of this smart inverter control, you can control everything: power factor control, voltage control here, active power control, reactive power control. And then once you will be controlling the active power, then you need to take the help of this DC link capacitor. So you should have a good design and good choice of that capacity of the capacitor. What should be the value? Therefore, this plus this capacitor, this will basically provide you the smartness. It will provide the required intelligence to control everything. So that's why it is called the smart inverter. Okay, so therefore, this is in briefly the dynamics of wind and then solar system when you have now, and we discussed that synchronous machine. Now think that in the system you have synchronous machine, you have solar system, you have the wind system. And now we want to analyze the transient stability. So that's why we need to look, we need to understand all the dynamics. So therefore here there are some sample questions for you for practice. Everybody see the first question, that during a network fault, how will the stability of a fixed speed wind generator and a variable speed wind generator be affected? Will there be any difference between the stability of these two types of generators? So for example, you have a system and you have a fixed speed wind generator, and then you have the variable speed wind generator. So therefore, what will be their stability level? You see, both are wind generator, but one is fixed speed, other one is variable speed. So if you look from the grid, how can you distinguish, or what is the difference between the stability level of those two types of generators? So in other words, which generator, either fixed speed on or the variable speed on, which one will be affected more, and why and how? So therefore the answer is that if you see the structure once again, this is the structure of the fixed speed. You know, they are directly connected to the grid. Here you see there is no power electronics component. There is no AC to DC, DC link, or this is the capacitor only. And keep in mind, this is uncontrolled capacitor. There is no controller. You see, this is fixed. So therefore, when you install this generator, at that time you have placed. I mean, why I am saying that, so that you don't argue that, no, you have capacitor that will handle. Keep in mind, this capacitor is only for the steady state. During transient situation, it will work, but it does not have much influence. It will try to do something, but it does not have control capability because this is uncontrolled. Plus, it does not have any power electronics equipment connected. So that's why during fault, so you see, as I said here, during fault in the network, rotary speed goes very high, active power output goes almost low, almost zero, and terminal voltage goes low or collapse down. So this will be the situation for the fixed speed wind generator. But under the same fault, if you have any of these structure or this structure which are variable, because you see there is power electronics component, this converter, they have sophisticated controller. Therefore, the first thing is that once there is any variability here, then because immediately you are converting into DC, plus they have the control capability, I mean, there will be some effect here on the grid due to fault, but this controller will help. That's why the variable speed wind generator are less susceptible. It will get less affected as compared to the fixed speed because they have the power electronics equipment. Those power electronics equipment will has that inherent capability that will try to maintain some stability. It is not like that it is fully able, but at least it will help you. So variable speed, typically it does not go out of control. Typically it does not go unstable situation. But fixed speed wind generator, like frequently they can go unstable situation because they don't have in between power electronics component. So that is the answer for this system. Once again, everybody look, how will the stability of a fixed speed wind generator and a variable wind generator be affected? Will there be any difference between the stability? So the answer is yes, there will be difference. A fixed generator, wind generator, the terminal voltage, speed, or everything will be severely affected. But variable speed generator will not be affected that much, or it will be slightly affected. Then why? Because they have the power electronics equipment connected between the generator and the grid point. So, could you follow everybody?
Yes, Dr. Ali.
Okay.
Yes, sir.
Yes. Okay. Great. Now the next question again regard to that stability. Like if a photovoltaic power generation system is connected to a grid, then during a network fault or heavy load condition, will the solar intensity of the PV generation system be affected? Will the PV terminal voltage be affected? So explain your answer. So therefore, for example, you have this system and then there is network connected grid and somewhere fault happened. And then you know the basic principle of PV, it depends on the sun intensity or solar intensity that produces the voltage or the power here. So therefore, do you think that grid fault will impact that intensity or that terminal voltage or power here? That is the meaning of that question. That will the solar intensity PV generation system be affected? Will the PV terminal voltage be affected? So therefore, what do you think? So Lakshmi. So if there is fault here, so will it affect this terminal or the intensity, solar intensity? I mean, why I am asking this question? What is the reason of that? Because when we have this type of machine, then because there is the shaft, whenever there is any fault on the system, not only the terminal voltage power affected, because impact goes until the shaft speed. We say the shaft speed go high or go low. In that way, we tell because this is that input side for this generator. That's why this is a static system, but its main power is dependent on that solar or sun intensity. So that's why I am asking that if there is any fault here, so what do you think that will that be intensity be affected or what will,
I
sorry?
I don't think so, Dr. Ali, because here the smart inverter will have the capability to control that deviations that are caused at the grid fault.
No, even though without the smart controller, you see, because that sun intensity is not directly connected here, right? It is coming through the air.
Yes, Dr. Ali.
That sun is not the part of the PV system, right? Yeah.
Yes, Dr. Ali.
Yeah. So therefore, even though without controller, without anything, you don't need to think about the controller. It is coming from the nature. So you cannot control anything. And even there is no physical connection. It depends on that sun intensity. It depends on the photons only. So therefore, whatever happen, everything might be affected, but it cannot affect that sun intensity. Same thing. If any fault here, the shaft speed will be changed, turbine will be changed, but will it change the wind? It cannot do anything with the wind because wind is coming from the nature. But this component will be affected. The same thing, the terminal voltage will be affected, right? So the terminal voltage will be affected. Now that you mentioned that with the help of the smart inverter, you can control. That is the next stage. That yes, you will be controlling so that you will not allow any change. That is different. But the question is that can the terminal voltage be affected or not? That was the question. That will the terminal voltage be affected? So the answer is yes, that will be affected. Solar intensity will not be affected. because solar intensity that is the nature that is coming from the sun. It has no direct physical connection with the PV. But the PV terminal, the voltage will be affected. Then that you said, if you have the smart inverter or control system here, or there can be controller at the grid level, or there is energy storage, they will help maintain the stability. So, do you understand?
Yes, Dr. Ali, thank you.
So therefore everybody say, not only like I said here, will the PV terminal voltage, actually everywhere it will be affected. You see, all are connected together, all are interrelated. So if something happens, then this point will be affected, impact will go here, that will impact here, and that the impact will go here. So therefore definitely until the terminal, the impact will go. Then the question is how you will handle, then that is the smart inverter or other mechanism. But due to fault, there will be stability impact here as well. Even though this is the static system, there is no rotating part. Okay, I think we have much more questions. So I like to stop here today because already we are over. So let's discuss in next class. Okay. So do you have any questions, comment, anybody?
No, Dr. Ali. Thank you.
Okay. Okay. Thanks everybody. So then I am stop sharing.